Hi everyone, my name is Juan Antonio Becerra. I am a telecommunication engineer as well as a PhD student at the University of Seville in Spain. I'm also an IEEE member and an MTTS member. I would like to talk to you today about the basics of power amplifiers. This video is divided into 3 parts. In the first part, I give a few basic definitions. In the next section, I will briefly explain the characterization of power amplifiers. In the last part, I would like to give an example of how microwave engineering helps us to solve a practical problem. An amplifier is a device designed for increasing the power of a signal by use of an external energy source. In an electronic amplifier, the input signal is usually a voltage or a current. Amplifiers might be classified in a variety of ways depending on their application, the frequency range they cover, or the active devices used. Ideally, an amplifier increases the power of a signal without otherwise altering it. Practical amplifiers have finite distortion and noise which they invariably add to the signal. Moving into the frequency domain, in an ideal amplifier the output is a scaled replica of the input. That's not the case when it comes to real amplifiers, whose output has several new frequencies, increasing the occupied bandwidth. This circuit is the evaluation board of a power amplifier for low-cost applications. This coaxial device is a 10 dB attenuator with a flat response in a wide range of frequencies. That is, it does not produce distortion to the signal. It is used to protect the receiver from dangerous high signal levels. This is a vector network analyzer. We will use it to measure the input versus output power relation or AM-to-AM characteristic. In a linear device, this relation is given by a constant gain that is displayed as a straight line, but this amplifier is a nonlinear system, and for a high enough input power level, the output saturates and the AM-to-AM characteristic is no longer linear, as shown in this experiment. This is a vector signal generator. It is used to create any waveform, in particular communication signals. And this is a vector signal analyzer. It will be used to show the signal spectrum. Now, we have loaded an excitation signal consisting of 2 tones on the signal generator. If we switch on the output port, the signal analyzer screen shows the spectrum of this signal. This 2-tone signal is now applied at the input of the device under test, driving the amplifier to a saturated level. These are the fundamental tones. These peaks are the third-order intermodulation products. These ones are the 5th order. Now we are going to test a digital communication signal used for a standard terrestrial TV broadcast. As you can notice, the bandwidth of the signal is 8 MHz, corresponding to 1 TV channel. Next, we apply this signal to the input of the power amplifier. As you can observe, there is a significant spectral regrowth, especially in the adjacent channels. This effect depends on the signal level. If we reduce the input level, the signal looks with lower spectral regrowth, at the expense of a very poor efficiency. Microwave engineering helps us to solve this problem by means of, for example, predistortion. Applying the inverse characteristic to the input signal, we can manage to get a linear output, avoiding the operation of adjacent channels. Of course, there is always room for improvement.